Lecture 25 of Numerical Methods is our second lecture about ordinary differential equations and their solutions. If you don't know much about the subject, you'll want to make sure you watch Lecture 24 first. We are once again going to get into the logistic model for population growth, looking at formulas for the solutions, their graphs, and how to interpret them. Then we're going to talk about our very first numerical method for approximating solutions to differential equations. It's called Euler's Method. Don't say Euler, say Euler. We will also look at the errors for Euler's method. So here's the plan for Lecture 25. So we will once again start with a review of the logistic model, talking about the basic setup, what do the variables mean, for example. Then we'll look at the solution using this method called separation of variables, which I did talk about at the end of Lecture 24. We'll need the method of partial fractions along the way, though I'm not going to dwell on that. I'll just say what the answer is. As far as my students go, we are ultimately more focused on numerical approximations in this class because it's numerical methods. However, talking about solution methods and formulas for the solutions is, I think, essential to helping you understand numerical methods because it helps you understand what differential equations are all about. We'll look at the graphs of solutions in the slope field. We'll make use of a solution to solve a couple practical problems. Then we'll ask a couple questions and try to answer them about the accuracy of what we did and how ideal it is or not to have a precise formula. Then we'll talk about Euler's method, the basic idea, visually, how to implement Euler's method with iteration, in other words, with a recursive equation. We'll do an example, quote unquote, by hand. Of course, I'll do it in the PowerPoint, but you should check things by hand with your calculator, and you should definitely have your calculator handy as we go. And we'll look at how to implement it on a spreadsheet. We'll look at the errors in the approximation. We'll talk about implementing in Mathematica, especially for my students. And then finally, I'll make some brief comments about interpolating numerical solutions to relate it to what we've talked about before. So what is the logistic model for population growth? Assume we have a population, say fish, okay? Because in a later lecture, like we did in Lecture 24, in fact, we're going to talk about harvesting, which means fishing. It's a population Y. Units we're going to take to be thousands of fish in a small lake. And we're going to assume it follows this model that I'll be talking about here in a minute. That's got a certain carrying capacity, L equals 1,000 fish, that essentially is our hypothesized limit for the sustainable population of the lake. And we're assuming this is true with no fishing. Again, later, in a later lecture, we'll talk about fishing. Assume time is in months, I could assume years, and that we have a continuous growth rate that is true for small populations. They're growing at a rate of 4% per month. The population model is the following differential equation. It's called first order because it only involves a first derivative. It's autonomous because the right-hand side of the differential equation is independent of time. It doesn't change over time. We'll talk later about other ones that do. It's nonlinear because the right-hand side function is nonlinear. It's an ordinary differential equation as opposed to a partial differential equation because it involves only ordinary derivatives. Here it is, y prime, or I will more commonly write dy dt, equals f of y, where f of y is this function of y. Now, if right away you would be scratching your head and be saying, wait a minute, how can a derivative of a function with respect to t be some function of y? That's the first initial thing that most people are confused by. I need to explain this as we go. But for the moment, don't worry about it. Plug in k equals 0.04, plug in L equals 1. You can simplify to this if you like, but let's focus on this part right now. As I emphasized in Lecture 24, this is the key to understanding why this might seem to be a reasonable model. When y is real close to 0, like 0.01 or 0.02 for example, y over L would be very close to 0, and 1 minus that will be very close to 1, making the product k times y times this very close to k times y. Now, of course, k times y is itself going to be a small number, but the more important thing is that would be a model, dy dt equals ky, that is an exponential growth model where the rate of change of the population is proportional to the population itself. The more fish there are, the faster baby fish are being born. They certainly overwhelm the number of fish that are dying. On the other hand, as y approaches the carrying capacity, there is less food available for each fish. More fish are dying off faster. Y over L is going to be close to 1. 1 minus y over L will be close to 0. This will not be as close to 0 when y is sufficiently close to L. Essentially, this expression is back down close to 0, and so the derivative, the rate of change, the slope of a solution curve has to approach 0. Probably there's going to be some kind of horizontal asymptote. In fact, there is, as y approaches L. Okay, so that's the basic intuition behind things. Remember that both sides of the equation have units of thousands of fish per month. Certainly the dy dt notation, the Leibniz notation here, emphasizes the units for the derivative would be thousands of fish per month, units of y per unit of t. Over on the right-hand side, it's got the same units. This thing inside the parentheses actually is unitless. It's dimensionless because you're taking thousands of fish per month dividing by thousands of fish per month, and 1 itself is unitless. K is in percent per month, y is in thousands of fish, so the right-hand side, if you convert the percent back to a decimal, can certainly be thought of as having units of thousands of fish per month. What is our goal? We want to find a functional model of how the population depends on time. We want to find a formula for a function that solves the differential equation, that is a solution to it. We're going to write such a function with different notation. We're going to call it y equals phi of t. Some people say phi of t, I say phi of t. You should be aware that many textbooks abuse notation here and write y equals y of t. That's not ideal notation because it's using the same letter y to represent both a variable name and a function name. That's what our textbook does, by the way, for my students, that uses that notation. But this is really a better notation. Here we are emphasizing y as a variable, but phi is just a function name. Y has units of thousands of fish, but phi is just a function name. It doesn't have units. It's not a quantity. T is still time in months. What does it mean to solve the differential equation? Well, to find it, we're first going to assume that our solution function, phi of t, which is different than the f function, that right-hand side function, okay, but they're related. We're going to assume it solves the differential equation, okay? dy dt equals f of y, and use separation of variables to solve it, to find a formula for phi of t, at least we hope. To understand what that means, you need to watch lecture 24. I will re-emphasize it here. It means when you take this function of t, plug it into the left-hand side of the differential equation, substitute, in other words, find its derivative, simplify, and then plug it into the right-hand side of the function in place of y to make the right-hand side ultimately depend on t, and simplify, you get the same thing. That's really, really key to understanding what it means to solve the differential equation. For any moment in time, phi prime of t really will equal f of phi of t, and both sides will be functions of t in that situation. So that's what you want to understand. Y is the function. You need to substitute this to the differential equation. And this equality right here is saying in symbolic form exactly what I just said verbally. Here's the left-hand side, phi prime of t. Here's the right-hand side. Remember, it was k times y times 1 minus y over L. K is 0.04, L is 1. I have replaced the y here and here with phi of t. This equation needs to be true for all values of t in some domain, typically near t equals 0, for this to be a solution of the differential equation. Now it's a matter of rearranging this equation to try to solve for phi of t. It's not going to be clear why this is called separation of variables. I will remind you of that at the end when we talk about thinking of this in terms of the Leibniz notation. So here's the next step. Divide both sides by phi of t times 1 minus phi of t to cancel it on the right and get a fraction on the left. You're just left with a 0.04 on the right. If phi of t is a solution, then this is going to be true for all values of t in our domain. We make the assumption that phi of t is a sufficiently nice function, like continuous, and its derivative is also continuous, then this function on the left-hand side we can integrate. It's going to be an integrable function, and we can integrate both sides, in fact. The right-hand side is easy to integrate. To integrate 0.04, you're going to get 0.04t plus some arbitrary constant. I'm going to call it c1. The left-hand side certainly looks harder to integrate, though. How in the world are we going to integrate that? Essentially, you can use a substitution. Typically, in Calc 1 and Calc 2, you use the letter U or W for your substitution, but here we are going to suggestively use the letter Y. If Y is phi of t, then dy in your substitution will be phi prime of t dt. The phi prime of t dt can be replaced by dy, and on the bottom you get a y times 1 minus y. The equation becomes this. Note that if we use the Leibniz form of the original differential equation, we're going to get the same thing when we separate variables. This is why it's called separation of variables. Here's what I mean. Start with the dy dt equals 0.04 times y times 1 minus y. Try to get all the y's on one side and all the t's on the other side. The d's just go with their respective variables. So you can certainly get rid of the y on the right-hand side by dividing both sides by y and also 1 minus y. And you can make the dt go on the right side by, well, treating dy dt as if it were a fraction and multiplying both sides by dt, which is called an infinitesimal quantity. This is not rigorous math, at least not in the ordinary sense of the word, when we're talking about the ordinary real number system. So it's kind of hand-wavy, but it does get us down to the same integral that we got in the previous line. We'd write the differential equation like this, and then once again integrate both sides. Okay? So don't worry about the rigor level of that. It's an intuitive way of thinking about the idea of separation of variables that, if you're careful, still gets you to the same equation. But we still need to integrate the function on the left-hand side. Hopefully, if you're taking Calc 2, you recognize this as something where partial fractions can be used, and that's what we'll talk about now. Remember that our goal is to find the formula for y equals phi of t. We already integrated the right-hand side of the differential equation and got 0.04t plus an arbitrary constant that we called c1. The idea here is we want to integrate the left-hand side, and hopefully we can algebraically solve for this unknown function, if possible. That integral on the left-hand side can be computed using the method of partial fractions from calculus. We want to rewrite the integrand function by breaking it apart into fractions like this. We want to, hopefully there's two constants, a and b, so that a over y plus b over 1 minus y equals the original integrand function. It should be intuitively clear that this might be possible. After all, if we add these two fractions by getting a common denominator, that denominator will be this product here, y times 1 minus y. So let's go ahead and do that. You can check if you solve for a and b, you'll find that they both equal 1, and therefore the original integral for the left-hand side is the integral of the sum, and you can integrate each piece individually. The integral of 1 over y is the natural log of the absolute value of y. The second piece is a little trickier. The integral of 1 over 1 minus y is actually negative the natural log of the absolute value of 1 minus y. That can be checked a couple ways. If you differentiate this and use the chain rule, the derivative of the inside function is a negative 1, which cancels with this negative sign when you're going back. On the other hand, if you do this integral with a substitution, like u equals 1 minus y, then du would be negative dy, and so you get a negative sign in here either way. Finally, the difference of two logs is the log of their quotient, and you can ultimately put the absolute value sign around the entire quotient. Now we set this equal to the right-hand side expression, 0.04t plus c1 from the previous slide. We want to get rid of the logarithm so that we can solve for y, so we exponentiate to get rid of the logarithm. And we get this. I get a e to the 0.04t plus c3 on the right side after exponentiation, where c3 evidently would be c1 minus c2. And then, by properties of exponents, that function can be broken apart like this, and I can call e to the c3 an arbitrary positive constant, at least, c4. Boy, it sure would be nice to get rid of those absolute value signs. Can you do that? It turns out you can. I'm not going to rigorously prove that, but the proof ultimately is in the checking of the final answer. If you get rid of the absolute value signs, you might write that y over 1 minus y equals c5 times e to the negative 0.04t, where c5 is an arbitrary constant, either positive or negative. We have excluded the case c equals 0, actually, but don't worry about that. Can we solve this for y? You can do the algebra. Cross multiply first. Multiply both sides by 1 minus y. You'll get y on the left side and c5 e to the negative 0.04t times, in parentheses, 1 minus y. You can distribute the c e to the 0.04t through the parentheses, rearrange, ultimately solve for y. This is what you should get. Y equals this expression right here. I'm going to go ahead and call that expression phi of t. And a final simplification that's often done is to divide the top and the bottom of this fraction by c5 and also by e to the positive 0.04t. Doing so gives this fraction, and now you just have one arbitrary constant. That arbitrary constant is related to c5. c is 1 over c5, at least when c5 is non-zero. once again, some magic is going to happen and our final answer will still work even if our initial condition is 0. And that's what we'll talk about now. An arbitrary initial condition, y of 0 equals y sub 0. Here already I'm moving away from my phi notation here, but don't worry about that. Again, this is traditional notation for the initial condition. Gives what? We can solve for c. Plug in t equals 0 right here. E to the 0 is 1, so you get 1 over 1 plus c, which is what you see here. Has to equal the initial y0, whatever number that happens to be. You want to think of that as a fixed number. Solve for c, flip both sides, and then subtract 1, you'll get this. And those two things can be combined by getting a common denominator of y0 to get this. You can substitute that back into the phi function and get this. And then do a final simplification, multiply the top and the bottom by y0 and write the final answer like this. And this even works when y0 is 0, because when y0 is 0, this is the 0 function. Its graph is the horizontal axis. That is a solution of the differential equation, you can check. It's called an equilibrium solution. It's a very special solution. This is the unique solution of the corresponding initial value problem that consists of the differential equation right here and this initial condition where I think of the y sub 0 as being a fixed number. It could be 2, it could be 3, whatever, 0.1, but it is fixed. Then I have a unique solution. One function satisfies both of these conditions. To emphasize the dependence of the solution on the initial condition, it can also be useful to write a subscript like this. Put the subscript right here. Y equals phi sub y0 of t, to emphasize that this does depend on what the initial value of y is. Okay? Again, you are thinking of y0 as being fixed, but it's unknown. So it's good to include it in the notation here. Okay? Don't worry about it too much. It's just emphasizing that this expression depends on y0 as well as t, though I'm thinking of t as being the main variable, so to speak. For instance, if y0 is 0.1000 fish, which would be 100 fish, then our population functional model could be found by plugging in y0 equals 0.1, and it gives you this. So we plug in a 0.1 here to get a 0.1 there. Here and here gives a 0.1 plus 0.9 e to the negative 0.04 t. Here are the graphs of various solutions of the differential equation in its slope field, which will also include this particular solution. That's the one that's in green here. This is the green function, phi sub 0.1 of t. This is a graph I showed in the last video, lecture 24. There are other solutions in here. This particular brown graph satisfies the initial condition that the initial population is 1.3 thousand fish, 1,300 fish. That's higher than the carrying capacity. The solution decreases toward the carrying capacity. If the population starts out real low, 0.01 thousand, which is 10 fish, it doesn't increase very fast at first, but then it starts increasing as the population level gets higher and babies are being born more rapidly. But again, both of these populations are leveling off. The derivative is approaching 0 because once we reach this carrying capacity or get close to it, then the environment can't support the population so well and more fish are dying off than before, and the rate of change of the population is approaching 0. This is an autonomous differential equation, and so its slope field has constant slopes along horizontal lines. What is the slope field? That's just a bunch of line segments that the solution curves must follow, in the sense that anytime they pass through the center of one of these little line segments, that line segment has to be kind of like a mini tangent line to the solution curve. And take this particular horizontal line at y equals 0.75. Both the green and the blue solutions have that slope, that rate of change, f of 0.75. where f was the original right-hand side function, which happens to be 0.0075. You can double check that, okay? Keep in mind the units here. This would be equal to the derivative at those different times for these two different functions. The units for this are actually thousands of fish per year, so that in terms of number of fish, that's about, or per month I should say, it's about 7.5 fish per month is the rate of change at those moments in time. T is in months here. We can use this model now to both make predictions about future populations and to solve for times when the population will reach a certain level. So for example, once again in the case where our initial condition is y0 equals 0.1 thousand fish, What is the predicted population 50 months in the future? How do you solve it? Just plug t equals 50 into the formula. Okay, so I already have a negative 0.04 there, a negative k. I already have my y0 here, and my 1 minus y0 there. Here's where I plug in t equals 50. Take the time to pause the video, double check this with your calculator. The answer is about 0.451 thousand fish, which is 451 fish. On the other hand, how long does it take? What does the model predict for how long it will take for the population to reach 900 fish, which would be 0.9 thousand fish? Set y equal to 0.9, keep t as unknown, and solve for t. You're going to have to rearrange and ultimately use a logarithm. So for example, if we multiply both sides by 0.1 plus 0.9 e to the negative 0.04t and get it on the left side, and divide both sides by 0.9, you'll get this is 0.1 divided by 0.9, which is 1/9. Subtract 0.1 from both sides, divide both sides by 0.9, and then take a logarithm. Haven't taken the logarithm yet. Here's the step of subtracting 0.1, 1/10 from both sides, and then dividing both sides by 0.9. Now take a logarithm. Ultimately, use properties of logarithms and divide by negative 0.04, and you get this expression, a couple negative signs canceled. You can double check that's about 110 months for it to reach 0.9 thousand fish, 900 fish, okay? And you may want to go back a few minutes in the video and look at the graph and see that these answers seem reasonable. However, we need to take a step back. That was quite a lot of work. Was it worthwhile? Here's some questions. Is it even accurate? And yes, was it worthwhile? Are there better and/or quicker ways to obtain the answers? Well, one quick answer to the second one is to use technology, like Mathematica perhaps, but we want other answers to that question. What about the first question? Its accuracy has to be tested against reality. All models are caricatures of reality. They don't match reality perfectly, okay? For one thing, when the fish population is approaching L equals 1,000 fish, there are still fish being born and still fish dying. So in reality, the graph should really be going up and down a bit. But we're oversimplifying it to keep it simpler, okay? Which is okay, but we still want to test it against reality. Maybe L equals 1 is wrong. Maybe it should be 2. Maybe K equals 0.04 is wrong. It should be 0.05 or something like that. Maybe the overall entire model is just not good enough, okay? And no value of K or L will work. You have to test it against reality. For the second questions, qualitative methods, I'm not going to talk any more about what that means in this lecture, maybe in a future lecture, can be determine what's called the long-term behavior more quickly. In a nutshell, qualitative methods help you figure out what the graphs look like without formulas and without numerical methods. However, they cannot be used for precise quantitative predictions for most values of time t. On the other hand, numerical methods can be used to obtain both precise predictions and hopefully more quickly get them, though they are not always better predictions. Okay, there's still this question of accuracy that depends on how well the model is doing against reality, for one thing. And for another thing, if we're bad in choosing our numerical method, maybe our approximate solution is way off. By more quickly, it is with a caveat. It's a caveat that you have to learn the methods first before you can implement them. And that's what the rest of this lecture is about. And Euler's method is our first method for numerically approximating solutions of differential equations. Euler's method provides a way of quantitatively approximating solution curves using a numerical iteration scheme with a recursive equation. The basic idea is this. For small jumps in time, how small is small? Well, it depends on the situation. Solution curves, the phi of t functions, should be well approximated by their tangent lines, right? That's a basic fundamental thing in calculus. If you've got a nice function, in particular if their derivatives are continuous functions, for example, tangent lines should be good approximations to the original graph. And the tangent line slopes can be determined from the slope field. In other words, by plugging in the second coordinates of points, the y coordinates, into the right-hand side function, the f of y function. That's how you determine the slope field. I didn't emphasize that a ton, but I really emphasized it in lecture 24. So here's a picture of a zoomed-in version of phi sub 0.1 of t, the green graph here. at time 0, if you plug in the second coordinate of this point, y equals 0.1, into the right-hand side function of the differential equation, you can double check, you'll get 0.0036 thousand fish per month. So about 3.6 fish per month at time 0. That is the slope of the green curve. That is the slope of its tangent line. And look, the green function is a nice function. Its tangent line in black is a good approximation to it, even out to about t equals 10 in this case. Okay, once you get past 10, then they're getting further and further apart. Euler's method takes advantage of this particular scheme. Here's the general setup. Suppose we're given an initial value problem. dy dt equals f of t comma y. This is something different for this lecture. I did talk about this in lecture 24. The right-hand side function can actually involve some t's. It can involve both t and y. This is a harder kind of situation. T is a variable. It's time. Y, at least in this setup, is a variable, though it ultimately depends on t. It's a function of t. It's the phi of t. To satisfy a differential equation like this, which is non-autonomous, phi prime of t, the derivative of phi, would have to be the same thing I get if I replace the y with phi of t in here. It would be the same as f of t comma phi of t for all t. That's what it would mean to be a solution. Watch the end of lecture 24 if you want to see an example of that. And we have an initial condition, y of a equals y sub 0. Usually a is 0 here, but we want to allow for a general initial value of t. We'll still call this an initial value problem, even though a might not be 0. We'll still call it that. Again, our goal is to approximate the unique solution. If there is a unique solution, you might wonder, is there a unique solution? That's a question for the next lecture. Phi of t over some interval from a to b. That's the overall setup and goal. So what do? Here's how you implement it. First, choose the number of steps, n. For my students, by the way, in our book, they use a capital N here, but I'm so used to calling it little n that I just couldn't resist. This is similar to what we did with numerical integration back 2 lectures ago, lecture 23. Though there are differences after this point. We're going to define a step size to be h equals delta t equals the length of the interval b minus a divided by the number of subintervals, n. I'm using 2 letters to represent this, an h and a delta t. I'm actually more used to delta t, but once again our book uses h instead of delta t. It doesn't matter. The important thing is to realize in either notation that it's a step size. From this point on in the PowerPoint, I will do what the textbook does and use an h. And define the so-called mesh points to be similar to what with numerical integration, endpoints of each of the subintervals. A t0 is equal to a, and then a t1 is delta t or h units to the right of t0. Then t2 is h units to the right of t1. Then t3 is h units to the right of t2. Etc. T sub I is a plus I times h for I equals 0 through n. If you plug in I equals 0, t sub 0 equals a. If you plug in I equals n times h is n times this thing. The n's cancel, leaving you with a b minus a plus b minus a is b. t0 is a, tn is equal to b, whatever a and b happen to be. All right, now we're going to talk about Euler's method itself. Setting w0 equal to y0. Not all textbooks do this. Our textbook does. So the w values are going to be approximations to the y values, but we want to keep them distinct symbols. Euler's method is defined by the following recursive equation. W sub I plus 1, the next value of w, is the previous value of w plus some change in w. And how do you find the change in w? This is where the geometry comes in. You take the slope at the previous value of t and w by plugging into the right-hand side of the differential equation, effectively evaluating the slope in the slope field, and multiplying times delta t, the change in t, which again we're calling h here. Say that again. The next value of w is found by taking the preceding value of w and adding on an approximate change in solution function. Take the rate of change times the change in t. H times this thing is the rate of change because that's what the differential equation is representing. The rate of change dy dt of a solution is equal to the right-hand side function anytime it passes through a certain point. In this case, we're talking about a solution passing through the point ti, wi. Okay? This takes some getting used to. Coming back to the previous picture here, if t0 is 0 and t1 is 25, now you'd never use an h equal to 25, okay? But if we did, then the second coordinate of this point would be w1. And it could be found by taking w0, which is 0.1, and adding on, trying to draw a right triangle here, adding on the length of this line segment, that would be the delta w, which can be found by taking the slope here, the 0.0036, times h, times 25 in this case. Now again, you'd never use an h that big, but just for the sake of illustration. What happens when you implement this? It generates n+1 data points. The 0th data point is essentially our initial condition. Okay, those are two things are equal to each other, two different symbols for the same thing. Then t1, w1, then t2, w2, etc. through tn, wn. Tn does equal b, but wn here does not necessarily equal the function value at b. It doesn't equal phi of b necessarily. It should make sense. This is just an approximation. The hope, though, is that it approximates the phi values well, that y sub I, which is defined to be phi of t sub I, is approximately w sub I. We hope this is a good approximation for all the values of I. And ultimately, you might say, maybe what we're most interested in is when I equals n, when ti equals tn, which is b. So we hope phi of b is well approximated by w sub n. That might be the main thing we hope. Let's now implement a couple steps of this by hand, so to speak, though of course you'd want to use your calculator to help you, to approximate the solution over the interval from 0 to 10. So a is going to be 0 and b is going to be 10. What is our initial value problem? Remember, we're going back to the logistic equation, so f of y is 0.04y times 1 minus y. Y sub 0 is 0.1 thousand fish, so that's 100 fish. Let's take n to be 2. Okay, so this is not realistic. This is for the purposes of illustration. N is too small, h is too big. H, or delta t, is the length of the interval, 10, divided by the number of subintervals, 2, which is 5. That's too big, but bear with me. Here's our mesh points. T0 is the initial value of t, which is 0, same as a. T1 is h units to the right, so it's 5. T2 is h more units to the right, so it's 10, which matches b. Furthermore, W0 is the initial value of y. It equals y sub 0. It's 0.1. Our approximation is exactly right at the initial condition. How do you find W1? Use the recursive equation. W1 will be the previous value of W0, which is 0.1, times the change in W, which is a product, h times f of W0, 5 times f of 0.1. F of 0.1 was 0.0036. We saw that in the slope field. We plugged the second coordinate, which we called y0 before, into the right-hand side function and got a slope of 0.0036. You can check that this is 0.118. Now calculate W2. It's W1 plus the change in W. Both of those quantities are going to be different than before. W1 is 0.118 now. H is still 5, but now we evaluate f of 0.118, and that gives us a slightly bigger slope, a slightly bigger rate of change. Double check when you simplify this, you get this. Okay, so there's our 2 steps of Euler's method. This is our approximation of phi of 10. Phi of b is this number right there. That's our approximation. How did we do? Well, again, we certainly did perfectly at the initial point. How about the others? If you plug in t1 equals 5 into the phi function, the solution, you get this. That matches this one fairly closely. If you plug in t2 equals 10, into the phi function, you get this. Also pretty close. Okay, so we're not doing too bad here. What are the actual errors in the approximations? Well, errors are always exact. I always think of it as a actual value minus approximate value. That goes in alphabetical order. That's the way I remember that. Actual minus approximate. So the actual values are the phi values. The approximate values are the w values. So the error at step 0 at the initial condition is 0. W0 minus y0 minus w0, 0. The error after one step is w1 or y1 minus w1. This minus this is approximately this, 0.0015 approximately. And the error after two steps is w2 minus y2 minus w2. Actual minus approximate is a bit bigger, but still pretty small, 0.00337,405. Euler's method is not too hard to implement in a spreadsheet. Let's do that now for n equals 20 and h equals 0.5 and see how it goes. Same problem, same differential equation, the logistic model, same solution we're trying to approximate over the interval from 0 to 10. But now we're going to break it into 20 pieces that are half units in length. Let's see how this goes. I'll make the spreadsheet available to you in the link in the description below. All right, so what do we have here? I'm just reminding myself of what the right-hand side function is of the differential equation. That's not a solution, it's just the right-hand side. You plug solutions into it in place of y. Taking n to be 20, y0 to be 0.1, a to be 0, b to be 10, I can change these numbers, and in fact I want to program the spreadsheet in such a way that if I do change these numbers, that things will get updated correctly. What is h? Type it in as a formula. It's b minus a, e5 minus d5 divided by n in b4. So that's going to be 10 over 20.5. That's the h here. All right, let's fill in the table. I is just keeping track of what I is, so I could start with putting a 0 there. Then I can type equals b8 plus 1. And that formula will get updated to equals b9 plus 1 to make this one a 2. Then b10 plus 1 right there to make that a 3. You see the formula up here, equals b10 plus 1. The copying and pasting of the formulas updates them if you don't use dollar signs for fixed cell references. I want to do, remember, 20 steps, so I do need to click and drag this down until I get to I equals 20. Not there yet, need to go 6 more. There we go, up to I equals 20. T0 is the initial value of A. I can type equals D5 there if I want to change A. That will get updated. So yeah, if I change this to a 1, for example, this gets updated to a 0. And that got updated to a 0.45. Let's go back to 0. I want W sub 0 as well. That is the function value at t equals 0, which is the initial condition. So this is B5. Make a column for h times f of wi. This is the trickiest one. Well, I guess I'm going to do the phi values as well. Careful here. H is in cell F5, but I want that to be a fixed cell reference, an absolute cell reference as I copy and paste downward. So I certainly need dollar signs in front of the 5. I also put it in front of the F to just play it safe. Okay, you want to play it safe to fix both the column and the row. Do double dollar signs like that. That's H, and the dollar signs will keep it to be an F5 as a copy and paste downward. Then I want to plug in Wi, which is in cell D8, into the function. Now there's no way to type this function into this spreadsheet without literally typing it in this cell right here. So 0.04, I guess I could have had a spot for the value of k as well, but it's not a big deal. Times y, which means times wi, times 1 minus y, which is 1 minus wi. And for those D8s, I do not use dollar signs because I want them to get updated to D9, then D10, then D11 as I copy and paste downward. Okay, so this is 0.0036 times 0.5, right? We already knew what the answer should have been. What about phi of t itself? Remember the formula was y0 over y0 plus 1 minus y0 times e to the negative 0.04t. You remember that? So here in cell F8, we're going to get equals 0.1 divided by 0.1 plus 0.9 times e to the negative 0.04 times t. I'll write the e as an exp for exponential function. Negative 0.04 times t. Where is t? T is in cell C8. And I want that to get updated to C9, C10, etc. So do not use dollar signs. And this matches W0, right, as it should be. W0 equals Y0. And the error is going to be 0. The error is the actual value minus the approximation. It's going to be 0 in this case, but it will be non-zero after this particular situation at the initial condition. Now we got to program the next line here. Careful. This number is going to be 0.5. It's going to be T0 plus 0.5, which is in cell F5. I better use dollar signs if I want that to stay fixed, and use a cell reference for that matter if I want to change what H is by changing what N is. So that's T1 is 0.5. Here's the key step of Euler's method. Take the previous value of W plus the change in W. That's the key step right there. That's Euler's method, its recursive equation. Now, copy and paste this formula downward. What's going to happen? Think about its formula up here. The F5 will stay constant. That is the H value, 0.5. But then the D8 will get updated to D9. So we'll get a 0.04 times D9, which is 0.1018, times 1 minus D9. Giving us this. Phi of t itself can be found by copying and pasting the formula from cell F8. That's going to have the effect of plugging 0.5 into the phi function. There's phi of t itself. This is hopefully well approximated by W1. And you can see these are pretty close. Copy and paste the error down. It's no longer 0, but it's still very close to 0. 1.446 times 10 to the negative 5 power. We should now be able to click and drag all these rows downward like this. What's our final approximation? Our final approximation is W sub 20 right there. I'll boldface that. That's supposed to approximate phi of, what was it? Phi of 10 right there. Boldface that. And there is our error right there. Boldface that. You can see they're pretty close. The error is still pretty small. 0.0030671. Going back to the PowerPoint here. And that's exactly what we see. Okay? Error sub 20. The error after the 20th step, I put one more decimal place in there. Actual value minus approximate value is this. What happened here? We increased n by a factor of 10 from 2 to 20. The error, if you recall from when n was 2, well, it's right up here, 0.003 approximately, added another 0 effectively, 0.0003, up to some rounding. It went down by approximately a factor of 10. Very interesting. I wonder if such an observation always holds, at least approximately. Can this be implemented on Mathematica? Yes, but it is trickier. It's best done using a built-in Mathematica function called nestlist that I'm going to show you how to use right now. There's one more slide in the PowerPoint after this. You may want to go forward to that if you're not interested in the Mathematica. Hopefully it's of interest to you even if you don't know Mathematica. Don't worry about the details. My students should worry about the details, though for my students, even though this is pretty complicated, you can copy and paste and make appropriate modifications. So here's the way I enter the initial right-hand side function. Here I'm entering a and b. Here I'm entering the value of h, which depends on n, so different n's are going to get different h's, just like we've talked about. This is the way of entering ti as a plus I times h, but notice there's a dependence of this on both I and n. These two lines here are the keys, okay? On this line, I'm creating what I'm calling an EM iterating function. EM just stands for Euler's method. This is something I'm creating. I'm just calling it this. EM iterating function. K and N are parameters that can change. W is going to represent W0, then W1, then W2, etc. This is the right-hand side of the recursive equation for Euler's method without subscripts. Okay, think about the recursive equation. It's W sub I plus 1 equals W sub I. This is like the W sub I without a subscript. Plus H, this is the H, it depends on N, that's why I need the N in there as well, times F of W. Okay, and the K just allows me to change the K. So this is a function that I want to iterate that is going to implement Euler's method. It's representing the recursive equation without subscripts. I can enter that. And here is where I actually use nest list. So nest list iterates functions, it applies them over and over again. So I want to apply this function over and over again. Enter this. And now, for example, I can plug in k equals 0.04, n equals 2, and the initial condition of 0.1 to get my approximation to the phi function first at 0, which is exactly right. Then at t equals 5, 0.118 was the value of W1 in that case. Then at t equals 10, this is W2 in the case where n is 2 and h is 5. If I move up to the case where n is 20, so that h would be 0.5, then I'm going to get a lot of more data points here. I get these data. This represents now 20 steps in Euler's method. This is W0, this is W1. This is now approximating the solution value at t equals 0.5. This is approximating at t equals 1, etc. Ultimately, this is approximating at t equals 10. This is W sub 20, 0.141822, approximating phi of 10. It would be good to get the times values in here as well. For example, when n is 20, 0.5, 1, 1.5, 2, etc. Ignore this one, I'll get rid of that. This is going to give me data points. So not just W values, but also with T is the point here. Data points. So now these are points, 0, 0.1, 0.5, 0.1018, etc. The last one at T equals 10 is the point 10, 0.141822. I'm doing this so that I can plot them in the graph with the solution function. All this code, which again you can just copy and paste, don't worry about how it works, and make appropriate modifications if you need to, like if you need to change k and plugging in k equals 0.4, y0 equals 0.1, you can make changes in those spots. Gives me a graph. The green graph is the solution phi sub 0.1 of t, and the black dots are the data points that are generated from Euler's method. And you can see that on this scale it looks like they're basically right on top of each other. That's not exactly true. There's definitely some differences here because of those errors being non-zero. All this code will generate a similar kind of thing, except now I'm letting b be 200. And in this graph, I picked the number of steps here. Let's see. EM data points to be back to 20 steps. B, the right endpoint, is 200, so now I'm going out further in time from 10 to 200. But here I am using fewer steps, only 20 steps over this big interval from 0 to 200. So H is actually 10, giving me 20 data points. And you can see there's a difference between the green curve and the approximation generated by Euler's method. You can visually see that it's not exactly right. It's too low down here and possibly too high up here. And by the way, it should make sense that it's too low and the graph of the solution is concave up because the tangent line is undershooting the graph. The fact that it's concave up here means the tangent line is below it. All right, on to the final slide. How should we connect the dots? Now I want to relate it to function interpolation. In other words, connect the data points. Use some type of interpolation. Lectures 18 through 22, we talked a lot about interpolation. Linear interpolation, where we're just connecting the dots with straight line segments, certainly could be good enough to get reasonable looking graphs. In fact, that might be what Mathematica did. And rough numerical approximations for the population growth model, which actually should be okay, because we shouldn't expect this model to be that good necessarily. It's not like a physics model that gives us real precise, accurate answers. Here's a couple graphs, same situations that I just showed you. And as a final point here, I just re-emphasizing what I just said. For more accurate models, such as you would encounter in physics using Newton's laws, for example, we probably would want something better than just linear interpolation. We'd want to talk about higher degree polynomial interpolation, as we discussed in lectures 18 through 22. Lagrange interpolation, Hermite interpolation would be better, maybe cubic splines, that kind of thing. Okay, so we'll ultimately be trying to connect these kinds of things in future lectures. Thanks for watching.